Hello everyone, welcome to David Griffiths Electrodynamics. My name is Brandon Beresford, and I'm going to be working on problem 3.31 today and kind of walking through the solution of this problem. So this problem is on page 156 inside of Griffiths textbook, the 4th edition. The problem statement says that for the dipole in example 3.10, it wants us to expand this 1 over script r plus minus term to an order of d over r cubed, and then use this to determine what the quadrupole and octupole terms are in the potential. So if we go back real quick to 3.10, I believe it's over here. Yes, so it's talking about this setup here where we have a physical dipole set up, and it kind of walks us through essentially how we determine, how we get this multipole expansion that this section is all about. And it goes through this whole thing, and you find out that, you can express the potential of any charge configuration as this sort of summation of these integrals dealing with these Legendre polynomials, essentially. And I think what it's asking us to do here is to expand to sort of go through this summation here, expand this term here, 1 over r, but, it wants us to do this 1 over r plus and minus here, and expand this and go through and not show, I think the monopole term would be the n equals 0. The dipole term would be n equals 1. The quadrupole term would be n equals 2, and the octupole term would be n equals 3. So it wants us to expand that out and kind of just show what these other terms look like. So I've kind of written this down. I drew out the diagram, and then I wrote down that equation that the 1 over script r is equal to 1 over r. And then we have this summation from 0 to infinity of this r primed over r to the nth power times the nth Legendre polynomial in terms of this cosine of alpha angle. And so I wrote down here that 1 over script r plus is 1 over r times the sum, and then this r prime term is the vector from our origin, which is this point here, to the actual charge. So in this case, to this plus charge. And that is going to be, well, this distance is d between the charges, then r prime is just going to be d over 2, and then r on the bottom. So d over 2r to the nth power, and then times the nth polynomial. And here we're just, instead of alpha, we're using theta here, where theta is the angle between, this angle here, defined for the problem. And then same for the r minus term. The only difference is that we have a minus cosine of theta here. And you can use this property that theta, we can essentially just use this property that because we're going to be dealing with angles on this side of the regime, that theta, instead we can redefine theta as 180 degrees plus theta. So I don't know, you could, I should have really maybe used a different variable here, I guess, like theta prime or something is 180 degrees plus theta. And so then we can define that cosine of theta is equal to negative cosine of theta prime, or however you want to write this out, I guess. But essentially you can get this Legendre, the argument here, in terms of negative cosine of theta. And there's a property that Legendre polynomials have where the nth Legendre polynomial of negative x is equal to negative 1 to the nth power times the nth Legendre polynomial without the negative sign in the argument. If you go look at Legendre polynomials in the book and kind of think about this for a second, it starts to make sense. So essentially, the even terms of the even Legendre polynomials, this -1 just becomes 1 because -1 squared is 1. So essentially only the odd Legendre polynomials get this negative sign for every nth power here. So that's just a property we're going to use because of this negative sign here. So anyways, we can write the potential as 1 over 4 pi epsilon naught q, and then times 1 over script r plus minus 1 over script r minus. So this is just sort of the basic definition of potential, the charge over the distance between them, and we're just summing those up. And then plugging in these expressions, essentially, we get 1 over 4 pi epsilon naught, q over r, which is common for both of these terms, and then we have the summation from 0 to infinity, d over 2r to the nth power, that's also common in both of these terms. And then, so we factored all that out, and then we have the nth Legendre polynomial of cosine theta minus p event, the nth Legendre polynomial with the negative cosine theta. And then using this property here, we rewrite this as the nth Legendre polynomial minus, and then -1 to the nth power times p of n cosine theta. And so if you actually think about this for even terms, this is going to be positive 1, and then you're going to have nth Legendre polynomial minus nth Legendre polynomial, which is 0. So all of the even terms in the sum go away, and you're just going to be left with the odd terms. So really our solution here is going to be, well, when it is odd, then you get 2. Instead of it being 0, these sum up, so you get 2 times the nth Legendre polynomial. So we can factor that 2 out, and what we end up having is 2 times q over 4 pi epsilon naught over r. We have this d over 2r to the nth power times the nth Legendre polynomial. So this is our expression now, and then we're just going to plug in what, for the octupole and the quadrupole. Well, the quadrupole term would be for n equals to 2, but we just saw that for even terms, the quadrupole potential term goes away. All the even terms are 0, so there is no quadrupole term. So our answer is that the quadrupole term is 0. Now for n equal to 3, which is an odd term, we should have a term here. So we're going to just plug in n equal to 3 here. So we're going to have 2q, that's a q, not an a, over 4 pi epsilon naught r. And then we have d over 2r cubed times the third Legendre polynomial. So that's 2q over 4 pi epsilon naught r, d cubed over 8 little r cubed. And then that's just doing this term here. And then the third Legendre polynomial in terms of cosine of theta is just 1/2 times 5 cosine cubed minus 3 cosine of theta. And so then it's just a matter of, I think I just canceled the 2 and the 1/2 and wrote it as just q d cubed over 4 pi epsilon naught times 1 over 8 r to the 4th power because of this r here cubed and this r here, and then 5 cosine cubed of theta minus 3 cosine of theta. So this is going to be our octupole term. And that's pretty much it. So that's pretty much all the book asks for this problem. So yeah, I hope that makes some sense. And I think really the key part here is maybe this simple this sort of relation here between the angles of cosine of theta and redefining the angle. So I would focus on that if that's tripping you up. But anyways, I hope you guys enjoyed this video. I appreciate it. Thank you guys for watching. If you guys have any comments, questions, or concerns, feel free to leave them in the comments below. And subscribe if you haven't already for more videos. And I'll see you guys on the next one.